starting from today, we start Module 4. Yeah. So last two modules, Module 4 and Module 5. Yeah. Module 4, two topics. First one, systems of ODE. Second topic, the first half of Fourier analysis. Because Fourier analysis, that's the main topic of our second half. After midterm, the most important topic is this Fourier analysis. So I split into two parts. First half in Module 4, second half in Module 5. Yeah. And we also need to, because we need to do our homework assignment number 3 as early as possible. Yeah, because we only have, starting from today, we may have slightly more than 1 month. Yeah, a little more than 1 month. Yeah, in this semester. But we have 2 homework assignments, number 3, number 4. So I need to use this limited time to give you 2 homework assignments. So I plan to, so this week, after this week I cannot. Yeah. So after next week, I need to assign you homework assignment number 3. Yeah. So then after that, then homework assignment number 4. Yeah. All right. Today I plan to do in this way. Yeah. All right. First, I want to talk about, yeah, so I'm grading your homework assignment number 2. I haven't finished it. Yeah. But I noticed several important problems I want to explain. Yeah. So first, I want to explain those. Oh, why I cannot select this? What's wrong? Oh, yeah. Oh, yeah. Oh, okay, it works. Yeah. There are 3 questions I want to talk about. Because in this way, after this kind of further discussions, we can learn better. Yeah. So 3 in my grading, I noticed these 3 questions. So we want to, understand better. Yeah. All right. The first question is this one. Number 4, question number 4. This one is pretty easy. So most of you got a correct answer. Yeah, almost all. Yeah. Right now, I did 3/4. Yeah, I did 3/4 of grading. Yeah, nobody missed this one. Yeah, but still there is one question. Yeah, so here I want to clarify that one. Yeah. All right. So for this question, yeah, most students actually they use existing result in the textbook. Yeah. All right. Here, this is the, I did a screenshot from the textbook. Okay, this result closely related. Yeah. So most of those students just apply this formula. Yeah. C is this. Yeah. So here, C is this. Wronskian, the value at x0 point. Yeah. So pretty much related to this expression. Yeah. All right. So the question is this. Yeah. All right. So here, in my solutions, I derive it. Yeah. But most of the students, they just apply the formula directly. Yeah. A few students, they derive it. Yeah. So when you derive it, we have this simple ODE. Yeah. So here, because we want to understand why this formula is correct, right? Yeah, we want to prove it. Yeah. And in this hint, it gives the idea how to prove it. Yeah. So we want to, go through it. Yeah. All right. Solving this simple ODE, everybody can do it easily. Yeah. So let's do it. Yeah. Separable, but when we solve it, there is one point we need to be very careful. That is this absolute value. Because when we do integral on the structure like this, we need to use absolute value, right? Yeah. The formula. Yeah. The formula, we should use absolute value. Yeah. All right. So the question, why? Why? Because in this formula, there is no absolute value. Okay? In that formula, there is no absolute value. So there is a small gap. We need to bridge that small gap here. So that's what I want to explain here. Yeah. All right. Why we can remove the absolute value, right? Yeah. So that's the question I want to talk about. So in my solution file, because at that time, I couldn't see a reason to remove. Now, when I wrote that solution, at that time, I couldn't see why we can remove it. So I put the sign here, but now I can see we can remove it. Yeah. Because this formula is correct. Yeah. This formula is correct. Okay? Yeah. But why? The question is, what is the reason we can remove? What is the reason the negative sign is impossible? Only positive sign is possible. Yeah. It would not happen for the negative sign. Negative sign case would not happen. Yeah. So we need to understand the reason behind it. Yeah. All right. Yeah. Let me explain the main reason why negative sign can never happen. All right. Yeah. Here, remember, there is one theorem we used in Module 2 about the Wronskian. Yeah. So Wronskian property. So let's review that theorem. Yeah. This theorem. Remember? Yeah. I explain. And I give you some concept questions related to this theorem. Now we need to apply this theorem. Yeah. All right. So this theorem, ODE1, just the ODE we are using. Q. That's the ODE1. All right. Yeah. So let's look at the conclusion first. We are working on some interval I. All right. Then, linearly dependent. Yeah. So here. Yeah. Linearly dependent. The condition for linearly dependent, if and only if this Wronskian is 0 at some point x0 in I. At some point, 1 point is enough. If this Wronskian takes 0 at 1 point of that I, then the whole Wronskian is 0. So here, right? Furthermore, if W equals 0 at 1 point, then W equals 0 on the whole interval I. That's the result we want to apply here. Okay? So 1.0 can force the Wronskian to be completely 0 on the whole interval I. That special result we can use to eliminate the negative sign case. All right, so to see it very simple, we just use a simple calculus result. All right. Yeah, so let me bring up the formula here. Oh, sorry. Yeah. So the formula, Wx, yeah, so for simplicity, Wx0. Wx0, our zero current is yeah, all right. So there are two possibilities, plus, minus. All right. Let's think about if it is minus sign. Yeah. We want to get a contradiction. Yeah. If negative what's that? Okay. If it's negative, can you see W of x and W of 0 have different signs? Can you see that? One positive, one negative, right? Different signs. All right. Then let's look at the contradiction. If they have different signs, we want to derive some contradiction. All right. Do you agree this W of x function is a continuous function? No problem, right? Continuous. Because it's differentiable, right? Because it's differentiable. Differentiable must be continuous, right? Yeah. Stronger than continuous. Yeah. So here we only need to use its continuity property. That's enough. All right. Because if it is continuous, there is one special theorem in calculus. Yeah. So very famous, yeah, but very fundamental. So that theorem called intermediate value theorem. So there is a theorem called intermediate value theorem. Okay, yeah. So people refer it to IVT, intermediate value theorem. Okay, yeah. So let's apply this theorem. All right. What's that? When you have a continuous function, here, let me draw a figure. Yeah. Here. Let's draw a figure. All right. For a continuous function, suppose we look at this on an interval, AB interval. This point is A, this point is B. If this function A point it's negative, okay? Yeah. The B point is positive, right? So this is negative, less than 0. This positive greater than 0, okay? All right. The function value, yeah. So let's say W, okay? Right. W of 0 less than 0. Here, W of x greater than 0, okay? There must be a point between A and B here, okay? There must be a point, intermediate point, okay, between A and B, such that W of that point, yeah, let me call W of x1, okay? So this point is x1. This point, its value must be 0. That's the intermediate value theorem, okay? All right. Now we find x1, yeah, because this interval, that's our I interval, right? Yeah. I interval contains 0 and x, right? Yeah. Because we are working inside the I interval. When we talk about W function, we work inside I interval. All right, so that's in I interval. In I interval, we find a point x1 such that, yeah, so here x0, but our x1 is here. So W equals W of x1 equals 0 in I, so it implies W equals 0 on the whole interval I. Whole interval I, but in our given condition, W of 0 not equal to 0, right? Yeah, it's a contradiction. Yeah. If we apply this theorem, W of x1 equals 0 forces W equals 0 on all the points in I. Yeah, we have this condition. W of 0 not equal to 0. So it's a contradiction. If it's a condition, that means the ratio cannot be negative. Yeah, we just take positive. Solve the negative case. Okay, yeah. So here, although it's some small problem, we jump some step. Yeah, because this step we jump, right? This step, So yeah, so we need to find the reason behind it. So that's our first question. Yeah. So later I will update this part in my solution file. Also in an exercise, remember the solution for the exercise question, yeah, related to this. So we can understand better. So that's the first question. Second question. This one, yeah, this one. I noticed several questions, not very big, but yeah, but I want to clarify, several common problems. Yeah. All right. Yeah. So most students didn't use this method, yeah, but a few students use similar method, similar but different from this one. Yeah. Because in our textbook there are two methods. Yeah. So the second one I didn't talk about in class, but I saw several students use the second one, but not the first one. Yeah. All right. Second one. Oh, sorry. Second one. Yeah. This is the second one. Okay. Yeah. So this is the second one. Yeah. Several students using the second one. Yeah. But most students just did calculation. Yeah. So very, long process. Yeah. So very messy. Things like that. Yeah. All right. So here, there are a few questions. All right. Yeah. So for the one important thing is most students only calculate IP, the particular solution. Yeah. Most students didn't give the IH, although it's not. Yeah, because I believe everyone knows how to calculate IH, right? Yeah. But when they wrote the solution, yeah, almost all of you only calculate IP. Yeah, and skip the IH part. Another thing is, in the question, we don't have the initial values, right? From the question statement, you cannot see the initial values, right? Yeah, yeah. But many students assume the initial values. Assume. So here, one is this one, another. Yeah, yeah. Many. Yeah, yeah. It's not completely wrong. Yeah. So if you use it correctly, still okay. Okay? Yeah. 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 But you need to, yeah. So I do not count it as a wrong. No. Yeah. Remember, Well, we can assume strategy will the golden rule. The golden rule of problem solving. Yeah, I mentioned in module 1, I talk about golden rule. The golden rule means when you have a relatively hard question, if you solve it directly, it could be very hard. Then you can modify, make it simpler. You can change the condition slightly to make it simpler. So you just solve a simpler version first. Then you go back to the original version. That's the golden rule. All right? So here we apply the golden rule. So we can modify the original question. So we add this assumption, no problem, right? Yeah. So we just add this assumption. Yeah. All right. So you solved a relatively simpler version of the original problem. Yeah. Especially several students use Laplace transform. Laplace transform, definitely you want initial condition like this, right? Yeah. Yeah. So 4 or 5 students apply Laplace transform to solve. So you need this initial condition. Yeah. So no problem. Yeah. But when you use this initial condition, your solution can only be this IP, right? Yeah. So it's not the general solution. So it's an IP solution. Yeah. So you find an IP solution. Yeah. All right. Yeah. Then after that, you need to go to the general solution, right? So after you find IP solution, okay, yeah. Next step, you need to find I solution equals IH plus IP. But when you add this IH part, yeah, I think for you it's very easy to get IH part, right? But when you add IH part, you remove that assumption. Yeah, because for your general solution, you don't need initial value, right? Yeah. So for the general solution, you do not need initial values. Yeah, that's the way we apply golden rule. Golden rule, after we find the solution of the simplified version, we need to go back to the original version by removing the extra condition we added. Yeah, so that's the golden rule approach. Yeah, yeah, yeah. No problem. Yeah, yeah. But those students miss this IH step. Although a simple step, but conceptually, you need to go that way, right? Yeah. In order to complete the whole solution, you need to add this RH part back. Yeah. So that's the common problem. Yeah. All right. Yeah. So yeah, then there is another version. These formula also given in a textbook. Yeah. So many students just calculate this version. Yeah. So also no problem. Just form looks slightly different, but the answer, same answer. Yeah. All right. But next, there is another concept, related concept. Yeah. So in the textbook, so let me show you. Yeah. All right. Here. Yeah. So this is the general solution. Okay. Yeah. So this is the the IH part. This is IH part. This is the IP part. Adding together. Yeah. But some of the students, when they write, when we write this RH part, they wrote 4 terms. Here we have 2 terms, right? 4 terms. 2 of the terms have this part. So same E function, same cosine, yeah, but just the coefficient part different. And the 2 of the terms have this part, yeah, but the coefficient different. Yeah. After you combine those 2 terms, you just takes new constant symbols, right? Yeah, yeah. So several students, you know, wrote the IH part in 4 terms. Yeah. So you can simplify a lot. Because here, C1, C2 arbitrary constants. So you have some relatively, you know, actually the coefficient is, you know, pretty messy, you know, 1.35, many digits, times constant C something. Then plus another 5 point, another, you know, ugly number times another constant, adding together. Yeah, the whole thing, you just use a new constant symbol, right? Yeah, that's another problem. Yeah, yeah. Or a small problem. I didn't take any point off. Yeah, just the expression, not the best expression. Yeah, yeah. For those problems, I didn't take any point off. Yeah, correct, because I believe it's correct. It's not wrong. Yeah. All right. Then there is another related concept here, based on the textbook. Yeah. So this paragraph I cut from the textbook. Yeah. All right. Because when you look at the solution, these 2 parts, first part, second part, okay? The first part, there is an E function. Second part, sine cosine, okay? Yeah. Their behaviors are different. For the E function, e to the negative 50 times t. Yeah. Think about, when t is very large, this E function goes to 0. Yeah? When t very large, that RH part approaches 0. That property. Yeah. Yeah. So almost disappear. Okay? Yeah. So then when t relatively large, basically what you have is the IP part. Okay? Yeah. So that is called a steady state current. This IP is called steady because this part steady. Okay, that part, you know, converges to this IH part converges to 0. Okay, yeah, almost 0. Yeah, so that's the concept of the steady state current. Yeah, if I use a graph here. Yeah, all right, upper curve. Transient, yeah, including IH part, right? Yeah, that's steady state current. Yeah, yeah. So this, you know, solid part curve. Yeah, steady state current. Yeah, yeah. I remember in one of the questions in our exercise questions, I copied the meaning of steady state. Yeah, actually at that time, yeah, because I searched from the web. If we read that paragraph, we couldn't understand. What's the meaning of steady state current, right? Yeah. But if you see the graphs of these 2 curves, now you understand. Now I understand. Yeah. Actually, at that time I didn't understand. Yeah. But after this example, now we understand the meaning of the steady state. Just the IP part. That's the steady state. Okay? All right. Yeah. So that's our second question in this, the last one. Yeah. Last one, this PDE question. Yeah. So this one, several students using the Fourier analysis way, Fourier series method. Yeah. So we haven't learned, yeah, but several students applied the, Fourier series method, solve this one. So I want to talk about these two methods, Laplace transform and the Fourier transform methods. All right. First, for the Laplace transform, in our textbook, there are some related formulas. So here, I don't want to get into the detail. So in our textbook, there is a exercise question solving the simplified version. Because here we have a capital H term. This question, there is no capital H term. So it should be simpler than our question. So that this capital W function is like this. So that it's easy to see this step. Then to get little w, here you using the convolution way. Because this is a product of two S function, right? F function, G function. Product. We can use the definition of the convolution, so we can write an integral for this little w function. So this way, at least, we have an integral formula, right? Although this integral formula is very hard to calculate, right? Because it depends on what is your little f function. For most of the f functions, you cannot find a nice function for the little w. Most of the time. But we don't worry about it. Because if we have an integral formula, we can always apply numerical values, right? So we have a numerical approximation formula. We can calculate integral. So here, we're very satisfied if we have some integral formula for the solution. Because we can do calculation. The bad thing is, because if for some bad capital W function, we may not be able to get a formula of its inverse Laplace transform, right? Inverse Laplace transform, if our function is not good enough, we cannot. Even to get an integral formula, very hard. But here, for the relatively simple case, we have the integral formula, although it's very complicated. The integral formula is pretty complicated, but we have the formula. Okay, all right. So that's one thing. All right. But then now you can see when this capital H term is added, it becomes harder. If you use Laplace transform, so your formula could be very complicated. All right. So then here I want to talk about the Fourier analysis. So those students who used Fourier transforms, the formulas calculated. But those students missed one important step. Here I do not go through the details. After we learn the Fourier analysis, then we revisit this question, so we can go through the details. Here, in our textbook, it gives the u function that corresponds our w function. Okay, u function corresponds our w function. Okay, it gives the Fourier series representation, and the capital A, capital B can be calculated in the given formulas. Just calculate integrals. Yeah. So those students just apply these formulas to calculate the result. Yeah. But so here I want to mention one important point. If they use this way, they missed one important step. Because this formula is for the version without this capital H term. Okay? This formula, given in the textbook, is for the version without that capital H term. No capital H. Okay? Yeah. Now, with capital H, you need to do some special substitution. Yeah. You need to use a new function, v function. You know, your goal is you want to convert it to a v function version without capital H. Without capital H, you can apply this formula. With capital H, you cannot apply this formula directly. Okay? Yeah. So the textbook gave us how to do the substitution. Yeah. So the formula given in the textbook, this formula. You introduce v function. Yeah. The relationship between u and v is this special, quadratic polynomial. Yeah. This special quadratic polynomial, so you can see if you plug into this equation, you will get Vt equals c squared v double x. H is gone. See? H is gone. Yeah? Because here, negative H, double derivative, x squared, 2, all right. 2, but you divide it by 2, right? Yeah. So you have 2, you divide it by 2. C squared, after cancellation, you have negative H and positive H cancel out. All right? Yeah? So for the v function, you remove that H term. Then you apply this formula on v function, not on u function. Okay? After you find the v function, then you just add this h part back. Add that quadratic polynomial back. Yeah. So that's the, this step. Yeah. Yeah. Those students. Yeah. So I look at, so they didn't use this step. Yeah. Yeah. Those students missed this step. Yeah. 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 All right. Yeah. So after we learn the Fourier analysis, so then we can go through the details, of all these formulas. Yeah. Yeah. All right. So that's what I want to talk about for the homework assignment number 2. Yeah. Yeah. All right. Yeah. Next we need to start a new topic. Yeah. So let's do it this way. How about we take a break right now and we start our second half